Okay, hi everybody. As mentioned in the logistic regression PowerPoint lecture, here I'm going to show you an example of how to do using the hardcore dataset. Uh, the example I've shown you on the PowerPoint slides, the results here will be a little bit different. I'll just tell you why. In there, I did not consider the assumption testing. Okay, I did not look at any assumptions. I plainly dumped everything in it and then got a result. Here I'm going to show you the assumptions texting first, and then move on. Well, as you know, we do not need normal distribution. Okay, please recollect from your PowerPoint lecture that we said it explicitly that we do not need logistic regression. We don't have to look for normal distribution. In fact, that's not an assumption at all. But some of the important things we need to see are the multicollinearity, outliers, and the linearity. Okay, so let's see how it can be done. So the first things first, let me look at the variable view. The first things first is what are the variables we are looking at? Okay, our independent variables will be from x1 to x7. Okay, and our dependent variable would be specification buying. As you can see from specification buying, there is two levels. One is specification buying, and the second one is total value analysis. So that will be a dependent variable. So what we are trying to determine here is this: depending on can these independent variables, can these 7 independent variables predict whether a particular company is going to go for specification buying or total value analysis? As simple as that. Now, the best way to analyze assumptions is a little bit different. The textbook doesn't tell you this way, but this is actually the best way to do it. Is actually go and do regression. Okay, so just plain old regression, analyze regression linear. Okay, in the dependent variable, select your specification buying as your dependent variable. Okay, and all your independents x1 to x7 as independent variables. It's very simple up till this point, right? Click on statistics, and here I don't care about model fit. I don't care about statistics because we are using this regression dialog box or the regression steps to just look at the assumptions, the linearity, outliers, and multicollinearity. I hope you remember some of the things that we discussed when we looked at actual regression with assumptions. Case-wise diagnostics 3.3 is better. Okay, and please select collinearity diagnostics. That's exactly what we need here. Plots, the same thing. The residual will go on the y-axis, and z predicton will go on the x-axis, and we need to see if they form into normal probability plot. Again, these are not your data. I'm not looking for normal distribution of the data, but rather the residuals. Okay, especially I'm using that to identify outliers. And here I want Mahalanobis distance, and that's pretty much it is in this case. Options, leave it as is. Okay, and okay. As I told you before, it looks a little different than compared to the other ones. The first things first is collinearity diagnostics. Okay, so if you remember, the tolerance should be less than 0.1. Okay, we see some of them which are greater than 0.1. Okay, and these should be 10, less than 10. Sorry, this should be greater than 0.1. They should be less than 10. Now you have 3 big values that are greater than 10. Now we don't need to go any bit lower than this, and this clearly shows that there is a huge multicollinearity problem here. And even if you want to see it, look at the correlation values, right? These are your collinearity diagnostics. These are correlation values. And you have to look for things. No, these are not correlation matrix. I'm sorry, we need to select for correlation matrix. I'm sorry, guys. Statistics, click on covariance matrix and you'll get correlation matrix. So I'm going to delete the previous one. Okay. Now, it's the same VIF matrix. There are 3 values which are greater than 10. We need to consider them and look at our coefficient correlations. And if you see, you should not have values which are greater than 0.7. Okay. And for product quality, everything is pretty well. For service, we have a big 0.975 with price level and a 978 with delivery speed. This is a big problem variable. Okay. Salesforce image, you have 0.766 here, and manufacturer image, you have 0.766 with the Salesforce image. Other than that, you will see that most of the other variables are fine except price level and delivery speed at 0.957. Okay. Now look at delivery speed, 35.747 VIF. That's bad, right? And look at the delivery speed here. It has a high correlation with 1. Price level 31.597, and you will see a high correlation with service, right? And delivery speed 43.854 for service. You will see a high correlation, 2 very big correlations, 9.7 and 9.8. So that's a big problem variable. We need to remove that even before we go further. And this is how you look at how if the PP plot is around the curve. If it is around this, you're in a good shape. Okay. Now in order for scatter plot, unlike regression where we are looking for a kind of a rectangle, here you need to have 2 horizontal lines at 1 and at 0, because those are your 2, not around 0. Okay. 2 horizontal lines, but again, it's not beyond 3.3. That is your cutoff. The moment it's go beyond 3.3 on x-axis or y-axis, that indicates outlier. In this case, it's in a good shape. Okay. Now let's go back to service. Now remember, I always say you take out one at a time. In this case, I'm suggesting you to take out service because it has the highest VIF factor. Analyze, regression, linear, take service out and run it without service. Now look at the VIF factors. Everything fell in place, right? It's all beautiful. Nothing is greater than 10. Interesting, right? Just one variable cleaned everything up. The reason is this: every other bad correlation is gone except the correlationship between Salesforce image and manufacturer image. 0.769, only 1 out of 30 values. Let's keep it. That's fine. Not 30 values. What? 5, 4, 3, 2, 1. It's about 14 values. Okay. So this indicates which collinearity is not a problem. This indicates it's a good linear relationship. Okay. And the G of X, remember this value is kind of a G of X. It's a good linear relationship and there are no outliers here. So we conclude that we are ready for logistic regression because the assumptions are clear, provided we did delete one variable, okay, because of multicollinearity issue. Now the next step is regression binary logistic. We remember we are doing binary logistic and we are not doing multinomial logistic for in this semester. Specification buying would be my dependent variable, my delivery speed, price level, price flexibility, manufacturer image. We will not use service. Salesforce image and product quality will be my other 2 variables. So in essence, we have about 6 independent variables. If you have any categorical variable, let's say you want to use this, please select categorical variable and then select accordingly. Okay, one of these could be categorical if you want. Save, group membership, that's pretty much what you need in this case. Unlike the SPSS file, here I'm selecting only group membership. Okay. Classification plots is very important. Hosmer-Lemeshow goodness of fit is a very important statistics that determines whether a particular model is indeed fit or not. I'm selecting that as well. Please include the constant in the variable. Correlation of estimates and iteration history, it's up to you. Confidence interval for exponential, this is for your actual odds ratio. What is the probability? Okay, and press. You can do enter. In this case, you can keep deleting one after the other because we're using the same significance model that we discussed. Otherwise, just use forward wall. You should be fine. Now, the first thing strikes the block 0. So what does block 0 means? Block 0 is there is no model, absolutely base model, right? That means there is no model. All we are using is what the data tells you. So as per this, if we do not use any specific model, we will be 60% accurate if you list everybody under total value analysis. Make sense? Because there are 60 people who are in total value analysis and 40 specification buying. So if I put everybody in total value analysis, we are 60% accurate. Sorry. Variables in the equation, we have no variables in the equation, and then there are 6 variables that are not in the equation. Now look at the significance levels of these 6 variables. These 2 variables, my belief is they're going to go off as it goes into forward stepwise. Okay, I repeat, because of the significance level, 1 or 2 of these variables will go away immediately. Now, these are the coefficient test of model coefficients, and it shows that if this thing is significant, that indicates that it's showing decent fit. That means the model, whatever the model is actually better than the base model. They're significantly different. Now look at the R square. The R square at step 4 is about 0.888, and even at step 3 is 0.862. That means your predictive model is explaining 88.8% of the variance of your final dependent variable. It's actually pretty damn good. In real world, it's pretty unlikely you'll get that. Hosmer-Lemeshow test. Now this is a test which pretty much tells you how good your model is with the prediction model. Now, as per the chi-square here, the chi-square value here should be, your significance should be greater than 0.05. If it is greater than 0.05, that means it implies that there is no difference between the observed and the predicted value. So it's actually saying that if it is 1, okay, if it is 1, that means the difference between observed and predicted value is nothing. I mean, it's 0.998 as model number 4. That is pretty damn decent. Here is step number 3. That's of caution. There is some difference, a lot of difference, in fact. Okay. The contingency table. So what exactly does it mean, right? The contingency table is what it tells you. It kind of groups the variables into equal number of groups. So in this case, 10 groups. It groups all the, not variables, sorry, all the cases into groups, 10 groups. So look at the bottom side. So if you were to identify specification buying total value analysis, that means step number 4, it's predicting everybody correctly. 10 groups and 10, average of 10 people being assigned here. So that is actually a very, very good state to be in. That means your model is doing its job. This number should be as close as it could be. If it should be over 8, this value should be over 8, and if it is 10. Okay, please remember that. Now, look at the classification table. Step number 1, you have 83% accuracy. Step number 2, you have a 91%. Step number 3, you have a 94%. And step number 4, you have a 96%. If you happen to remember what happened in the PowerPoint slide, there were only 3 steps, first of all. Step number 3, step number 2 had a better accuracy than step number 3. In this case, because we cleaned everything up, everything fell clearly. Now, look at the variables in the equation. The step number 1, it just took the product quality, and step number 4, it has delivery speed, price flexibility, sales force image, and product quality. All of these variables are less than 0.05. See that significance? That means it's a pretty good model to use. All these are less than 0.05. Interestingly enough, the product quality has a negative relationship, okay, whereas the other 3 are positive. Now what this means is delivery speed, 1 unit of increase in delivery speed will account for, any guesses? Please think about it before you answer yourself, I guess. 1 unit of increase in delivery speed will increase the 1 unit increase in delivery speed makes it 3.668 times more likely to classify a particular case into group 1. In this case, total value analysis. 4.127 for price flexibility, 10.464. That means Salesforce image is actually performing the best. That 1 unit of increase in Salesforce image feedback makes it 10.4 times, 10.5 times more likely to classify a particular case or observation into group 1. In this case, total value analysis. Whereas the product quality is negative, right? So do this as a simple calculator, use a simple calculator and try to assess this. 1 divided by 0.075. 1 divided by 0.075. I'm using a calculator right now. 0.075. So 13.33. So 1 unit of increase in product quality will make it 13.3 times more likely for particular case to be classified into group 0. In this case, specification buying as is. Okay. I hope using this you're able to understand how things are happening. I'll repeat very quickly what we did. First, what we did is we ran a regression to see which of these to make sure the assumptions are working well. The first thing first, what we did is we did a VIF. We checked on VIF, and you see 3 big VIF values over 10. So we eliminated service, which has the highest VIF factor. Then reran the regression, everything fell in place. And when we looked at the correlation values for values over 0.7, because we eliminated the bad variable, we have only 1 value, which is over 0.7. If you happen to remember the outcome, we don't have manufacturer image. Instead, we have Salesforce image that's predicting the best. Okay, this high correlation actually speaks for itself. Then we looked at residual statistics. Actually, we didn't look at residual statistics. I'm sorry, guys. Another thing we have to look at here is Mahalanobis distance, 13.746. Now, how do you get the critical value of Mahalanobis distance? My suggestion is go on Google. Mahalanobis distance critical value. Okay. Wikiversity, that is the best one, and here is the first file. This is what you need. Okay, now just let's look at the values here. Now, what is degrees of freedom? Earlier during regression, I did not explain the degrees of freedom. Now, if you happen to Google what is degrees of freedom, how to calculate degrees of freedom, generally speaking, they call it n-1, meaning if you have 6 independent variables, you need to select your degrees of freedom is 5. 6 minus 1 is equal to 5. The explanation of degrees of freedom is beyond the purview of this class, but just as very quick primer, your degrees of freedom is nothing but how much freedom does the variables have I repeat, how much freedom does a variable have in order to make sure that it's trying to fit the model or trying to evaluate the outcome. In this case, we have 6 variables, so we need to remove one, in order to see that there is, unless and until we remove one, there won't be any freedom, right? In essence, that's true. Okay, in essence, that's completely true. But in this case, we do have an error function. Okay, we do have an error function because we're actually using a kind of regression to see how things are going. We have a residual also. So my suggestion would be is there are different schools of thought for this. My suggestion would be consider degrees of freedom as the same as the number of variables. I repeat, degrees of freedom as the same as the variables because we do have an error function which kind of gives you that additional leverage to work on, additional freedom for the variables to work on. So in this case, I'm going back to this. I have 6 variables, right? So my critical value is 22.46. So anything less than that, I'm in a good shape. Look at the Mahalanobis distance maximum value. Okay, 13.746. So again, there is no outlier here. There is a good linearity. We have a decent look of it. So literally along the line, the PP plot. And the dependent variable, the residual plot, the scatter plot, it should be horizontal preferably, but it's not here. Still okay. There is no value beyond 3.3, 3 or 3.3. So there are no outliers. So we conclude that the data is in a good shape to run logistic regression. Then we ran logistic regression using a forward step method. I think forward WOD they call it. And the first things we look at is the the model summary, R square. It's a pretty good R square, 0.888 for step number 4. Hosmer-Lemichaud test is 0.998, which shows that there's a very good relationship. There is no difference between the predicted and the observed values. Okay. Then we looked at the contingency table where the ideal scenario is this is nothing but the number of groups in the data. I'm dividing 10 groups into 10 groups of 10, and towards the end of the step, you should be able to see that it's pretty identical. Okay, very close, meaning out of 10 groups, if there are 10 people who are going to say they are part of whatever this category is for specification buying, you should be able to predict pretty close to that. In this case, it predicted all 10, so it's pretty good shape. Classification table, which actually confirms how much are actually being predicted correctly. 96% for step 4, 95%, 94% for step 3. So step 4 is indeed the best. Here are the variables in the equation. We looked at the R value, the beta value. This is for your G of X. Remember, that is your G of X. Converting that into exponential, this is your pi of X pretty much, e to the power of b. And 3.668, what this means is any unit of increase in delivery speed makes it 3.668 times likely for a particular case to be assigned under group 1. Okay. Whereas for product quality, any increase in product quality makes it 1 divided by 0.075, which is 13.33. 13.33 times more likely for a particular variable to be categorized under group 0. That concludes logistic regression. Please repeat. I'm going to post the assignments. I want you to do the same HATCO assignment with validation sample as well. Create a sample of validation and the real sample, 60 and 40 or 50 and 50, however you deem fit. And I want you to run a repeat logistic regression using validation sample as well. Thank you.